So this is our last lecture on digital electronics. We're just gonna introduce some basic fundamental concepts on digital electronics. It's Boolean algebra and logic gates. So these are all examples of some logic gates. That performs any mathematical and many functions for processor. So first of all, machines only understand the binary language, and with only two states, on means one and off means zero states. So that's how machine understand any language, Any feature, any number, decimal numbers will be first converted to the decimal, to the binary numbers, something like that. Here's an example, and then machines will read that actually. And uh, what device performs that job. So again, it's the transistors, especially the MOSFETs. So the transistor work as micro switches. It's a microscopic switches which turns on and off, creating all these logic gates. So the very first thing to understand is it's called OR gate. It's also called logical addition. It's an addition gate, logic gate. So its logic gate works like this. So it's a two input logic gate, and this is the symbol for OR gate. It simply means A plus B, and this is something called truth table. So you have two input A and B, and since it's a logical addition, the output will be on, output will be high if one or two of the inputs are high, right? And output will be off only the output will be off only if all the inputs are off. So and and these are the rules. So A plus A, that means high plus high is high. A plus 1 is 1, right? A plus 0 is A. And A plus B is B plus A. They are commutative and they are distributive. So these are the rules we should know. So you can extend the same concept of OR gate to any number of n number of inputs. So again, same thing. OR gate works like that. If one of the input is high, the output is will be high, and the output will be off or low if all of the inputs are low. So something like that. So that's the main concept of OR gate. So how do you make the logic gates? So you have to first understand the transistor action. Remember, this is a MOSFET, N-channel MOSFET transistor is the power supply which provides the bias voltage, and the resistor is connected back to the ground. Output is taken here, and this will provide the gates voltage. So for example, if the gate voltage is zero, what will happen? So if the gate voltage is zero, right, the transistor will not turn on. Transistor will be in off state. So this is equivalent to a off switch, something like that. So the output will be zero. So if gate voltage is zero, the voltage across this resistor R2 will be zero because there's no current through the transistor. Transistor is in off state, right? Because transistor need the gate voltage needs some threshold voltage, right, to turn the transistor on, something like that. So that's how the transistor simply works as a switch here. Similarly, now if you apply the gate voltage, which is greater than VT, the threshold voltage, and let's say this is called you call on state. If the input is on, so this will then turn the transistor on, and since there's a flow of current, there will be output voltage. So output will be on, right? So you will have some output voltage. So output will be high. So it is then when the transistor is on, it is equivalent to so on switch, something like that. So that's how transistor works as switches. So how do you make the OR gate that we just discussed? In a symbol by actual using actual transistor. So that's how you make. So you need so this is a two input OR gate, and you need two transistors like that, and this is a drain source, so their sources are connected to the common points. So the sources, right, source terminals are connected in parallel, and again you need a regular resistor here, and you take the output here. So, and it works like this. So it if one of the gate voltage is on, it will turn that particular transistor on, and you get the output as on, but in order to get the output as zero, both gate voltages must be zero, and then this output will be zero, right? So next logic gate is called AND gate, and AND means product multiplication. So it's a logical multiplication gate, and this is the symbol for AND gate. So it's a two input AND gate, and its mathematical equation is so output C is A times B. It's a multiplication, and its truth table in terms of low and high. You know, a truth table will be something like that, and you can clearly see, right? The output will be high only if all the inputs are high. So that's the main logic behind it, right? In order to get the output high, you have to get all the inputs high, and these are the rules. A times A is A times 1 is A times 0 is 0, and commutative and then distributive, right? And so same thing, you can extend to the any number of inputs. So this is an example of three input AND gate. So A times B times C, and again the output output will be, see here, the output will be high if only if all the inputs are high. That's the main logic. So how do you make that AND gate from the transistor at basic level? So you need two transistors connected in series, something like that. So the source of the first transistor is connected to the drain of the another transistor, right, in series. And again, the output is taken across this R2 resistor. And here you can now clearly understand, right? If one of the gate voltage is zero, off, right, this will cut off the transistor, this one of this transistor, and the current through this, they are in series, the current through this transistor is zero, then output will be low if one of the gate voltage is low. So in order to get the high output, both gate voltages should be on, right, as you can see, because they are in series. So next logic gate is called NOT gate. So it's the logical inversion gate. It inverse. So if you provide A as input, so it will invert, and this is the symbol for complement. It's also called complement of A. So if this is A, the inverse of A is just the complement of bar. A bar means just the complement bar inversion. So its truth table is very simple. So if you input is 0, output will be 1. If input is 1, output will be 0. And these are the rules. So A complement is 0. Okay. A plus A complement is 1. And A double inversion is A. Okay, these are the rules that you should know. How do you make the NOT gate from the transistor at basic level? So this is how you do. You just based on the previous logic gates, you just move the register from source to the drain side. So you just, now you have to take the output here. So what's going to happen if you provide the gate voltage, right? The transistor will conduct, right? And the voltage, if you take the voltage here, it will be zero. So when the gate voltage is on state, when gate voltage is high, the output will be low. Why? Because since the transistor conducts, and since the transistor conducts, the voltage between this terminal with respect to ground will be zero. All the voltages will be here. So, however, if the input is low, if there's no gate voltage, then the transistor will not conduct, and all this voltage, this bias, all this bias voltage will appear here. Why? Because the transistor doesn't conduct. So that's how it inverts. It works as a NOT gate. So, and these are some basic summary of the basic rules of Boolean algebra. Used in digital electronics. And here's another gates actually. So once you know AND OR gate, so the next gate is NAND gate. NAND gate means the inverse of AND. So the inverse of AND is NAND, and you just put a circle here at the output. You have an AND gate with a circle at the output. That means it's a not AND, which is NAND. So, and this is the logic behind that, and it's the inverse of the AND gate. So that's why it will produce main logic for NAND gate is the inverse. I mean, the output will be low if all the inputs are high. And similarly, the second one here is the inverse of OR gate, which we call NOR gate. Not OR is NOR gate, and the main logic is the input will be the output will be high, if all the inputs are low. That's the main logic. Okay, and the next gate is it's called XOR gate. The XOR gate, and this is the symbol for special symbol for or XOR gate. And these are the two input A and B, and the output is A, or XOR symbol is this. And the main idea, the main logic behind this, mathematical logic behind this is this. So you get the output 0 off, right? Output will be off if all the inputs are same. If A and B, all the inputs are same inputs, then it will output 0. So if both inputs are same, right, it will be the output will be 0. If one of the outputs is different, then it will produce the high output. So that's the main logic behind XOR gate. And how do you make the NAND gate? So this is how you make the NAND gate. It's just like a AND gate, but you just move the register from here to here and take the output here. And this is how, and you can calculate how it works, and you can imagine how it works, right? And how do you make the NOR gate? Similarly, you just need to put the two transistors in parallel. So you connect to the join of these two. The source of these two transistors are connected common and path to the ground. And again, resistor is put here, and the output is taken across here. And the output will be, not OR, right? Not. You have to make the not OR. So okay, here's some example that I can show how the logic gates work. So implementing this logic gates action in a real silicon wafer, real silicon, in integrated circuit is a little different than individual transistor. In reality, actually, in in the given wafer, in the given chip, silicon chip, in an integrated circuit, thousands and thousands of this transistors has to be fabricated once, one flash in using, it's called CMOS technology, complementary metal oxide semiconductor. So here's one example of making inverter using CMOS technology. So in CMOS technology, it uses both type of transistors, P channel and N channel transistor, instead of just N channel or P channel, because it's more, economically more feasible and more easier to fabricate. That's why the CMOS technology is the most, popular technology these days for integrated circuit fabrication. And here's some example, of CMOS, making these logic gates using CMOS, and you can just take a look. I'm not going to go any detail on that. Okay, the next important theorem is, DeMorgan's laws. So it's simply, these are the only, it has two laws. So first law is, the complement of the sum is equal to the multiplication of the complements, right? And the second is the complements of the multiplication, complements of the product is equal to the sum of the complements, right? That's what the De Morgan's laws says. And it is basically used to simplify the logic gates, So using De Morgan's laws, you will see actually you can significantly, simplify the logic gate actions. So for example, here, x plus y inversion, right? So you first, what you need first you need x plus y, so you need OR gate. So x and y are the two inputs, so its output will be x plus y. So now you have to invert it, and this is the symbol for invert, not gate, right? And it will be invert, so output z will be this. Now this is, it says, according to DeMorgan's laws, this whole logic circuit, right, is equivalent to this. So you need the product of the complements, right, inversions. So first you have to invert x and y using a NOT gates, and then you AND it, and then you multiply it using an AND gate. And this is equivalent to that according to DeMorgan's law. Okay, and the main reason is because sometimes it's very useful if you just use AND or NOT gates, just make all the logic circuits using AND and NOT gates, or NOT and OR gates, and the same thing, second law, is similar. Second law, you can compare this logic circuit and this logic circuit are same. So the again, breaking down the DeMorgan's theorem graphically, visually, you can imagine something like that. So you have A and B, right? Product, complement of the product A and B. So how does it work? You should break this long bar, just break it and sum it. So that's how you can imagine, right? You can now, it's easy to understand like this graphically, to understand DeMorgan's law. So if you have a B complement, you break in the middle here the long bar and you add them, right? And this is equivalent to this, right? According to DeMorgan's theorem. And another example, if you have complement of the sum A plus B, right, you break this long bar at in the middle, and then multiply them. So this will be removed. If you break it here, you will have A complement, B complement, and multiply them. So this whole thing is equivalent to this according to DeMorgan's theorem. So let me give you more example. So here's an example. So if you have this thing A plus B C complement and the whole complement, right? So how do you break it? How to simplify it? So using DeMorgan's theorem. So you first break this long bar here, breaking the longest bar, right here, and based on the DeMorgan's theorem, right? This, if you break this here, this will be this thing complement times the, and double complement gives you BC. So this whole thing is equivalent to A complement times B times C, right? And the gate equivalent is this, the logic gate equivalent is this. So this is the first one, output, which is equivalent to this, right? So you just need an and NOT gates. See, remember, here you need an OR gate, AND gate, everything, right? But here, now, if you use, since this is equivalent to that, according to DeMorgan's theorem, you just need an and NOT gate, right? So some more example, as in just an example. So this three-terminal inputs, is made from OR, and NOT gates, right? And this is the output. This is the very final output. And since you need a, OR gate, NAND gate, AND gate, and NOT gate, so this will be, you can break it down, based on the DeMorgan. So you break the long bar first, and it will be this, and from here to here, the double bar is gone, and this again, the double complement is gone, and this can be written as distributive. This is the distributive properties, and A times A is A, right? And here B times B prime is 0, right? And finally, this whole thing, this long expression is significantly simplifies to finally just A times B complement, right? And in logic gate construction, it will be a lot easier. So this whole complicated logic gate construction can be just reduced with just and NOT gates. You just need and NOT gates to, construct everything, right? So the DeMorgan's theorem laws basically, simplifies the logic circuits. And sufficiency of NAND and NOR gates. So you just need NAND gate or NOR gates to construct everything actually, basically. So here's an example. So any logic function can be realized using only NAND or NOR gates. So if you want an inverter, you just need NAND gate. So you just short these two input, NAND gate short, right? And output will be A prime. So how do you construct AND gate from NAND gate? So you have two inputs. So the output will be the A times B complement, and you need a two input short together, right? Like this, A times B, and it will be double inversion, A times B, double inversion. So double inversion give you A times B, right? So this works as an AND gate from NAND gate. So how do you construct OR gate? Then using DeMorgans. So first you need from a NAND gate, right? So first you invert it. Using a NAND gate, you can invert it. You just need to short these two inputs, and then do the same thing inversion. And then this is again a NAND gate, right? A prime times B prime times that is equivalent to A plus B from De Morgan's theorem. Remember, so it basically says to make any logic gates, you just need AND and NOR gates, right? So here's some. This has nothing to do with any problem. This is just an example of logic gate action in any given circuit. That's how it works. So just turn the switch on and off somewhere, and it performs some logic gate actions, right? Something like that. And here's one more thing. So again, remember we talked about that in the very beginning. Machines only understand the binary language with just one and zeros. So for example, how do you convert 25 into one and zeros, binary numbers and numbers, right? Decimal to binary number conversion. It's a very simple one. So just keep dividing, since it's a binary number. So you have to divide by two. You have to divide the given decimal number by 2. So keep dividing by 2 and put the remainder, right? And all the way last remainder. And you read up, right? So the conversion of 25, the decimal number 25 to binary conversion is like this. After putting all these remainders, you read up. So the 25 is equivalent to 11001, right? And the machine can actually, the computer can understand this as 25. So how do you do the opposite? So how do you convert binary numbers to decimal number? And it's also simple. So first put the, so this is, say you're given the binary number 11001, right? Which is basically 25. Let's check actually. So put them like this, 11001, and you start from, so multiply the given 1 with the 2 raised to the power 0. Start from 0 plus, and 0, this 0 times 2 raised to the power 1 and 2 and 3 and 4, and add them all together, and that's gonna give you the decimal equivalent of the given binary numbers. Okay, so that's the simple thing you have to understand. So I have some sample problems, so you can try the same thing, and same. So these are some problems, and that's all.